Butterworth and Chebyshev filters their approximation function. This means that while the result is not acquired, is this close to accuracy. The Butterworth filter is one of the basic electronic filters designed to produce the flattest possible response of the cutting frequency. In the other words, the output remains constant almost to the cutting frequency. Then decrease and the rate of 20 n dB per decade, where n is the number of the poles in the filter. The most basic Butterworth filter is the typical first order low pass filter, which can be modified to a high pass filter on a date in series, other forming a band pass filter on removed band and filters for high orders. Advantages and disadvantages of the Butterworth filter. The advantage is that Butterworth filters have a response curve as fast as possible at the zero frequency point, minimum ripples, and is the only filter that maintains is the sharp to larger orders, only with a higher slope from the cutting frequency. The disadvantage is no relative slow it decays in the transition region. It decays at a rate of approximately 20 dB per decade, where n is the order of the filter. This filter needs higher order of the same requirements compared to Chebyshev. This is the transfer function, which G is the gain of the filter, W omega is the frequency, W omega sub C is the cutting frequency, and N is the order of the filter. Now let's see how we can do the filter order calculation. This usually determined for the required characteristic is the filter template, as indicated below, based on the attenuation specifications as the seen here, and that we do is divide them together and claim for the filter order, and it looks use a look on the right. Now let's see how we can do the calculation of the cutting off frequency. For the calculation, we have the two conditions before, and depending on which conditions, the chosen conditions, the epsilon value will be different. In principle, we will use the passband condition as long as the opposite is not specified. For this condition, the value of epsilon squared will be as below, and with this can replace in the equation of the cutting frequency, and it will look like this. Already with these equations, we can make a design for a Butterworth filters with MATLAB. We are asked by this exercise, which asks us to define the degree of a maximum flat step law function that satisfies the flowing characteristics. 1,100 kHz passband with a maximum attenuation on 500 milledecibels. Also an dimmed band of the 7 kHz and minimum attenuation of the 23 decibels. Ready to start, we can find the order of the filter with the equation above seen. Replace and give us 1,99, but as we know the order of the filter must be a natural number, we round it to 2. Now, since we have the order of the filter, we can find the cutting frequency with the equation we can before. It takes in account that this frequency is hertz and this time to pass it to rings per second as seen here, and there if we replace in the equation of the cutting frequency and give us 1561 hertz, which move be in the 3 decibels below the high hertz amplitude. Now, with the help of MATLAB, we can create the transfer function as seen here in the code, and this shows us this transfer function, which the graph into check if it's okay. As you can see up here, at 1,100 kilohertz, the maximum attenuation slow be 500 millibels and is in 918. This may be cause the calculation discrete decimals please use as in the attenuation band. Now we can find the resistors and capacitors to implement the circuit, which the second order Salenke transfer function. We can match the value you gave us in this and clear for the capacitors in this way, and knowing that resistance 1 and 2 are going to be a kilo ohm. As we can see, the capacitor 2 is 144 nanofarads and the capacitor 1 of 72 nanofarads. What was done was to check in a simulator this configuration with the value and graph as seen of the right, which the value graph was equal to the MATLAB chart. Ready, now let's look at the Chebyshev filters. This one gets a more pronounced frequency response of a low frequency because the allow cutting is the in one of its band. Unlike the Butterworth filter, there the poles are distributed over our circumference. The poles of the Chebyshev filter do so on an ellipse. Their zeros are on the imaginary axis and have the skin of response. The Chebyshev type 1 filter was the following characteristic. They are filters that only have poles. They have constant cutting in the throw band. They have a monotonic drop in the mom passing band. And your SPOF in frequency have this from. And in which the polynomial meets the following characteristics. The polynomial is between minutes 1 and 1 for a frequency between 0 and the cutting frequency in the passband. So that the safe function oscillates everly between 1 over 1 more epsilon squared. There are many methods to define this polynomial. An intuitive method is to make in the form of a signs as shown here. So that's what Chebyshev's polynomials will look like. Now with that we seen above, we can find the equations for calculating the order of the filter and epsilon, which is the curly. Ready as the first parameter, we will find epsilon occur, and this is calculated from the expression of the transfer function. Seen about that will like this. Now to find the order of the filter, we must keep in mind this equation, which is the minimum attenuation in decibels, and the expression of the polynomials to clear the order of the filter that will like this. Already with these equations, we can make a design of a Chebyshev filter with MATLAB. We are asked by this exercise, which asks us to find the function of transferring a pass-low pass Chebyshev filter that meets the following specifications: 1200 kilohertz passband with a maximum attenuation of 500 milledecibels, als a dimmed band of 1900 kilohertz and a minimum attenuation of 23 decibels. Ready, then the first thing is to calculate the curly value and then apply the equation of the precalculate order. Values are replaced and curly give us 3049 millis. And now if we apply the filter order, which they only replace and calculate, and we are 490, but as we now that the order of the filter must be a natural number, so it's not ro- rounded, rounded to 5. Already with these two data, we can get the transfer function with the coefficients of Chebyshev for a filter with the specification, the maximum attenuation of 500 decibels and a curly of 3049 millits, and this will be transfer function on fifth degree. Now in MATLAB we can see the graph. This will be the code to test the filter and be able to graph in as seen on the right. At 1200 kilohertz, the maximum attenuation shall be 500 milledecibels and is in 400 millits. This may be caused in the calculation decimals where the species use use in the attenuating band booting, but it is very close to that is required.